Okay, we're starting. So we're going to go over another method today, another integration technique. Usually it's not that, it doesn't take that long to apply, and probably in general will be easier than trig sub. But for me to describe the method to you is actually going to take a long time because there are many cases that you can be faced with. So we're going to be doing what's called integration by what's called partial fractions. So the idea is the partial fractions are really just smaller fractions that make up one bigger fraction. So example, we can talk about partial fractions of something that looks like this. So I can be given a larger fraction, but if I can break that up into a sum of new fractions, these guys are called the partial fractions. So that's what partial fractions is. They're the smaller fractions that can make up a bigger fraction. And so there are times when you have a bigger fraction and it actually breaks down into this kind of decomposition. We call it the partial fractions decomposition. And so this thing here is called partial fractions decomposition. So that's the idea. So we're going to do integration by partial fractions. So given some bigger fraction, we will describe a method by which you can take that bigger, more complicated fraction and break it down into smaller, simpler fractions called partial fractions. The idea behind this, of course, is if you want to integrate this guy, it's exactly the same as integrating these guys. And integrating this guy is difficult, but integrating each of these is actually no problem. What's the integral of each of these? It's just each of these are ln. Whereas this one technically is also an ln, but sometimes the fractions are more complicated than that. I could have also done something like a nicer example where it's not, this one you could just do a u sub in the denominator, you actually get the top, but there are cases when that doesn't work. Like for example, what if it was that guy? Then it turns out you could break that up into two parts where it's something over x plus 1 and something over x plus 2 as well, right? And each of these are easier to integrate than that, right? So that's the idea. So that's kind of the gist of it. But the thing is, there's so many situations you can end up in here. Like there's so many ways to have a fraction, and and so the decomposition, there are many situations in which you would break it down differently. But that's kind of the idea. Yeah?
Do we need to know what something is to integrate properly?
Yeah.
Okay.
Yeah, so I'm going to give you a method on how to go from a larger fraction to a bunch of smaller fractions, and how to actually find these numbers here. Okay. This one I could actually even tell you here. So this should be a 1. And then this would be a -1. Right? You'll notice that if I add these two together, I would get that. Right? Now this one you might not know how to integrate because it's not clear that there's an ln involved because the numerator is not the derivative of the denominator. But breaking this guy down into those two, then each of these, the numerator is a derivative of the denominator. So that's one example here, right? But how to do this can vary drastically, and it depends on the fraction that you have. Okay. So the idea, the integral of some big fraction is going to be the integral of its partial fractions. And this guy is easier to deal with. For example, if you wanted to integrate this guy, it's like, what? At this point, pretty much the only thing you could do with a guy like this is to complete the square and do a trig sub, but that's going to be ugly. But if you could see, for example, that this guy is really just but if you could see ahead of time that this guy is really just that guy, then forget trig sub. You can literally do that pretty easily. That's just ln of x plus 1 minus ln of x plus 2. Right? Very simple, right? Now going from this to this is called finding the partial fractions decomp. And that's a whole process to itself. So this lecture, or the remaining of the lecture, will be devoted solely, we're not going to focus on the integration for now. For now, we're going to focus solely on the process of going from this to something like that. Okay? So finding partial fraction decompositions. Okay? But this is the idea. It makes certain integrals a lot easier, and it can avoid a lot of headache. And once I describe the method in totality to you, you'll realize it's actually surprisingly easy to go from this to that, as opposed to actually completing the square, going through a trig sub and back substituting to get to that. It's going to be a lot less intensive. But that's basically the idea. So partial fractions are smaller fractions that you break up a bigger fraction into. This can help us with integration. So now the method has many steps, and there are many sort of things to consider. So I'll kind of go through each step and sort of give you examples while doing each step, so you can kind of see how things are breaking down. So here's the thing. So in step 1, for this method to even work, the powers in the numerator and the denominator have to sort of have a certain relationship to each other. So step one. The degree of the numerator must be smaller than the degree of the denominator. If this is not true, then use algebraic manipulation or you can use polynomial long division. Hopefully you remember that because I'm just going to kind of do it. I'm not really going to teach you that, guys. Or the equivalent of polynomial long division is called synthetic division. You might have learned that. Right? It's pretty much the same as long division. Personally, when I was a little kid, I learned about polynomial long division. I never saw this method until like way after, so I'm sort of partial to this one. I'll pretty much do this one all the time, except if you know this method is completely fine. I'll know I'll know the method when I see it, but I always forget. There's a sign change that happens somewhere. I never remember where it happens, and so I just kind of avoid it and do this one. Okay, so you can actually simplify a case where the degree of the numerator is larger than or equal to the degree of the denominator. It turns out that breaking into partial fractions, this method will not work. So step one is to make sure that that does not happen. So let's give you an example here. So example, let's say I had x squared over x squared plus 4. Okay. So now, in this case, notice that the degree of the numerator is the same. Let's say, I just want to call this something through of p of x over q of x. So you'll notice here, if you're given this, your degree of p is equal to your degree of q. That's bad for this method. So there are a couple ways you can do this. One, you can use algebraic manipulation. It will be a lot easier than long division if you can see it, and you'll see it with more practice. The more you practice this, the better you'll get at it. But it's really nice. It's kind of like the equivalent of knowing how to factor by FOILing as opposed to always going through the AC method. It's a shortcut. Whenever it pops up, you can use it. So one way to deal with this guy, for example, would be to try to get the denominator in the numerator. So in the denominator, I see an x squared plus 4. So what I'm going to do is I'm going to want an x squared plus 4 in the numerator. But could I just add a 4 like that? No. So what I would do is I would subtract 4. So algebraic manipulation here would take the form of adding 0 in a convenient way. So now what happens is I have the denominator now in the top. Right? So one way is to get denominator in numerator. Now you can accomplish this by something like adding and subtracting something, or multiplying and dividing by something. You don't want to change the value of the fraction, you just want to change the form of the fraction. And so now what you can do is you can actually split this fraction into two parts, right? You can split this into x squared plus 4 over x squared plus 4 minus 4 over x squared plus 4. So this thing splits into 1 minus 4 over x squared plus 4. Right? And so now you've broken up this larger fraction into two numbers where one number isn't even a fraction and the other number has the required form. The degree of the numerator is now smaller than the degree of the denominator. So now the degree of p is smaller than degree of q, and that's exactly what we want. Now, if the goal was to integrate something like this, we pretty much don't have to do anything else. This is in a nice form for an arctan substitution, right? So this guy would give you 2 times tan inverse of x is going to be the antiderivative of that, and x is of course the antiderivative of this. Okay. So if you were to have to integrate something like this is really as far as you can go, but there are times when the guy that you get here is still something you want to break down further. Okay. So that's one way you can deal with a fraction. Another way you can deal with this is long division. So I'm going to describe this for you guys. So basically what we have is, we have x squared, and I'm going to divide it by x squared plus 4. And so what we can do, you take the first guy, divide it into the first guy, x squared divided into x squared, the result is 1. You take that 1, you multiply everyone here, and you put it below. And then you subtract it. So the x squared kills the x squared, and then this becomes a minus 4. X squared into this you can't, and so this ends up being the remainder. And so this gives you the fact that x squared divided by x squared plus 4 is 1, which is the quotient, plus the remainder over the divisor. So this is just me using long division on polynomials, right? So if you remember long division from in regular arithmetic, let's say I wanted to divide 27 by 2. It's the same idea. You say 2 into 2 goes 1 time. Take that 1, multiply by the 2, it goes here. You subtract, that dies, 7 comes down. 2 into 7 goes 3 times. Take that 3, multiply by the 2. 6 here, subtract that, you're left with 1. 2 into 1 you can't, so that ends up being the remainder, so the answer is going to be 13 and a half. Right, it's the same long division, you're just doing it with polynomials. That's algebra class, I don't want to spend too much time going over that. So either you learn long division, polynomial long division, brush up on that, or you can do synthetic division. But in either case, the goal is to go from this situation to a situation where the numerator, the degree of the numerator is less than the degree of the denominator. I can do another example here. So if this were x cubed over x squared plus 4. Now let's not worry about integrating this yet, because integrating this is actually not that bad. A regular u substitution would work even in this form. But say, you can make it even worse like by doing that. So substitution would be a little harder now. Okay, so again, it's kind of harder to manipulate here. Right, because now to get the denominator in the top, you need to get an x squared in the top. So you're going to be adding and subtracting x squares as well as adding and subtracting 4s, and it's not going to be a nice time. So I would jump straight into long division if I see this. Right, so this kind of thing works best. There are other times when you might see it, but it works best if the degrees are actually the same. Right, and then you don't want to go through long division. Here, when the degree is actually larger, it's a little harder to do that manipulation, because then you have to, like, you might have to factor things. It's just probably not worth you taking the time to see it. You might as well just jump into the division. So this is like I have x cubed and I want to divide by x squared plus 4. The idea is, remember in long division, you kind of have to leave the positions for all of these guys. So there's a 0x, and then there's a 1 here. And so you say x squared into x cubed goes x. Take that x, multiply everyone here, you get x cubed plus 4x. Subtract, the x cubes die. Now you're ending up with minus 4x plus 1 from this guy. Well, let's make sure it ends up. This guy comes down plus 1. X squared into 4x, you actually can't, right? So this guy ends up here being your remainder. And so this would mean x cubed over x squared plus 4 is actually equal to x plus minus 4x plus 1 over x squared plus 4. Right? And now in this situation, the degree of the numerator is smaller than the degree of the denominator. Do we have any questions on this? So it's one of those things like when you're doing the method for completing the square, the numerator, the coefficient of the x squared term must be 1 because the method just won't work otherwise. Because we're taking advantage of patterns where it has the numerator has to have a smaller degree than the denominator. Right? So once you've rectified that situation, that's the first thing you want to look for. You're faced with a fraction, you probably don't want to do trig sub on it, and at the same time it's not clear that a u substitution would work. You might consider doing partial fractions in that case. And the first thing you want to look for is how the degrees match up. If the degree of the numerator is not smaller than the degree of the denominator, you cannot do the method. You have to break it down somehow. Algebraic manipulation or long division can work. Step 2, once that is complete, right? So once you're in the right form, the degree of the numerator is smaller than the degree of the denominator, you want to factor the denominator. More algebra. You have to remember how to factor, like factor in general. Why its factors will form the denominators of the partial fractions. So, an example here. Going back to that guy we saw before, you see that guy? It already has step 1 complete, so the next thing you will do is you would factor the denominator. So this I would notice that this is x plus 2 times x, sorry, that was a 2, times x plus 1. That's it, that's step 2, factor the denominator. Once you're in the right form, you factor the denominator. Now it turns out there are many ways that this denominator can, there are many cases that can happen in the denominator. So you factor the denominator fully. Right? We all know there are cases where you can factor and then one of the factors can factor further. So you factor the denominator fully. So that'll be step 2. Step 3. Split this fraction into partial fractions. The thing is, we don't know what the numerators would look like at the moment, so the numerators will be arbitrary, but they must be 1 degree less, exactly 1 degree less than the factor in the denominator. are more stipulations to consider, but that's going to be the basic idea of what you're aiming for. You're going to break this into a bunch of fractions where each of the factors in the denominator is the denominator of one of those fractions, and the numerator is some arbitrary expression that is 1 degree less than the denominator. So what do I mean by that? So let's say example. So if I have 1 over x squared plus 3x plus 2, the first thing I would do is I would factor this into x plus 1 times x plus 2, and the next thing I want to do is to break this up into two parts, where the factors are here, and the numerator is 1 degree less. So here I put a and b to represent arbitrary constants. Notice that constants are 0 degree polynomials because the denominator is a first degree polynomial. So 1 degree less than a first degree polynomial will be a 0 degree polynomial. Here, a, b are called arbitrary constants. Sort of like in your integration concept. Note, a, b are 0 degree polynomials. Constants are 0 degree polynomials. Another example would be, let's say I did the factoring and I ended up with something like this. X squared plus 7 times x plus 1. Now I would break that up differently, right? So there are two denominators to consider here. There's that x squared plus 7, and then there's the x plus 1. Right? Now, x squared plus 7 is a second degree polynomial, which means on top I need to put a first degree polynomial, which means I wouldn't just put an a here. In this case, I would put an ax plus b. I have to put the general form of a first degree polynomial because the denominator is a second degree polynomial. And then I would just have to put a c here. Right? And this can get as large as you need to. So if I had something like, and you have to make sure that this guy actually doesn't factor further. The sum of squares you can't factor further. Right? If this was an x squared minus 4, I would just factor again and then break it down into x minus 2, x plus 2, and x plus 1. But the fully factored form has a quadratic in it, so the numerator must be linear. I could also be in a situation where radical 2 or something strange like that. I could get in a situation where in the fully factored form, I have a cubic, and so when I put these guys here, the cubic, I need a quadratic on top. So I put ax squared plus bx plus c. And then over here, this is a first degree polynomial, so I need a 0 degree on top, so I put a d. Any questions on this part? Yeah.
So wait, why do you write ax squared plus bx plus c?
The denominator is a third degree polynomial, which means the numerator has to be a second degree polynomial. You have to put the most general case that could possibly happen. If I only assume this was an x, it is possible that it breaks down into an x squared. So I have to keep edging towards the x cubed without actually being x cubed. Because once this guy hits x cubed, I have to do long division and just kill it, right? So which means the next step down is the x squared, and so that's what I'm going to assume. Right? It's possible that I can solve for this and the a is 0 and I don't need it, but you never know. Right? So we always assume that the numerator is 1 degree less than the denominator. And of course the goal is to find these arbitrary constants. What are these numbers a, b, c, and d? That's going to be ultimately what we want to get to, but there are still more situations to consider. So this is 3b. If a factor has multiplicity. Count up to. That's not meant to be descriptive, that's kind of meant to be just a cue for what you know how to do. I'm going to show you what I mean by count up to. So the idea is the following. So what if we had something like 1 over, here's x plus 1, that's one of the factors in the denominator, but it's squared. And you have another denominator. How do you deal with such a situation, right? Now, you might initially start to break this down into 2 parts, which wouldn't be wrong. But now, technically, this guy is a quadratic, right? Even though the factor is linear, it has multiplicity too. So technically, it's a quadratic. So you'd want to write a linear function on top. But because the best way to do that, you'd think of this guy as just your variable, as the new x. And so what you would do is you do something like a times x plus 1 plus b. Right, so that things will simplify nicely. But what happens then is that this guy is going to break down into 2 parts. This will be a over x plus 1 plus b over x plus 1 squared. And then this would be a c. So you'll notice what happens in the case of a repeated factor, right? So this guys, I might refer to it as repeated factors. In the case of the repeated factor, I just keep copying that denominator, and I'm going to literally count up to the multiplicity. So let's say if this were something like, so example. Let's say I had 1 over x plus 1 cubed times x plus 2. How I would break that down is into x plus 1 squared, x plus 1 cubed. Right? I'm literally going to count up till I hit that power, because this sort of thing will happen. Right? It'll always happen like that. And then I put it over the x plus 2. Now it's important that the numerator follows the inner guy. So the inner guy is still a linear factor, it just has multiplicity. So my numerators are still going to have degree 0. Note, numerators follow the inner factors. Okay. And so the partial fraction decomp of this guy would look something like that. Let's do another example. Let's see if you guys are following me, because I've been talking for a long time. Okay, what about this? How would you break that guy down?
A over x squared plus 1 plus b over x squared plus 2, I mean times to the 2. That thing squared, and then plus c x squared plus 1 cubed, and then d c over x plus 3.
I appreciate the attempt, but it's wrong. What's wrong?
It doesn't have to be ax and bx because it's x squared.
Our factor is a quadratic. Do not forget the rule. The numerator must be 1 degree less than the denominator. So the factor I'm looking at here are quadratics, which means my numerators for all of these fractions need to be linear. They need to be first degree. So close but no cigar, we kind of had to make sure that the numerators obey the rules. So instead what it would look like is ax plus b over x squared plus 1 plus cx plus d over x squared plus 1 squared plus ex plus f over x squared plus 1 cubed plus g over x plus. That would be the generic partial fractions decomp of this guy.
Wait, why is it, so how do you get ax plus b? Like, why is it that and not just like ax?
Because you want the most general form,
Okay.
right? There might be a constant, I don't know, so I just put it there as a placeholder. You have to hold all the, you have to use placeholders to hold everything, because you never know how a fraction might break down. You don't know ahead of time.
Okay.
So we know that once the numerator has the same degree or larger, we'll use long division to break it down. So the very next thing it could be is when the numerator is 1 degree less than the denominator. And so I assume that all factors are accounted for. If it were the case where it's only an x, I would end up solving for the b, I'll end up getting 0. But you have to account for everything. Everything has to have a placeholder just in case it's there. It's possible for it to be there, possible for it to not. Any other questions? And we are out of time. Let's see. Okay, so there's literally more, technically there's like one more step to talk about, step 4, but step 4 is actually pretty hefty, so I'm not even gonna mention it yet.
So, factoring the
So
numerator.
at now we actually know how to break it down in an arbitrary sense. In the next class I'll teach you how to, the best way, I'll teach you 2 main methods, how to find these constants, find their values. Yeah.
So factoring the numerator completely doesn't mean we don't have, like. doesn't
Factor
mean
the
we don't-
denominator.
Sorry, the denominator. Maybe doesn't mean we only have, linear x's. Means it doesn't.
Right, you don't have to have linear factors. That's
Okay.
not,
As long as we just can't do it anymore.
yeah, just factor until you can't factor it. It's fully factored. Then break it up based on the numerators are 1 degree less than the denominator. And if you have a repeated factor, you have to count up to that factor, because a process like this is what happens in the factor. So next time we'll look at how to find these numbers and hence how to actually break down one fraction into a small.
So no homework.
No homework. No.
Thanks.
So is the quiz just on 7.1 and 2?
Yeah, quiz on 7.1 and 2. I'll probably put a bonus on this stuff. And maybe even a bonus where you go all the way and you find the constants. Who
So
knows?
the school's closed.
Huh?
7.3.
Wait, they canceled?
What's
No, no,
7.3?
It's going to
I think
be.
so.
Oh, I thought you said it is.
It's definitely
Sorry,
gonna
that's
be.
so much
It
I
might
wanted
close,
to-
I don't know. What's 7.3?
I spent 5 hours getting
It's,
home on Fridays. I'm not fit if it's
homework.
not.
Yeah.
So, because I take the train and, there was.
Okay, yeah,
You live in
so,
the
So yeah.
city?
No, I
so
live,
that is,
um,
so this is
it's just
7.4, right?
Oh, okay.
Yes.
Yeah, so 7.4 not due, but the other homework.
Suspended
Is
also was
7.3
somewhere
included?
along the
They're
line,
worse.
yeah, it was awful.